we have just one important point to finish the first week. This is the third lecture, so we just finish maybe 10 or 20 minutes, the last point from the first week, and we go on then to completely different story, but still linear algebra practically, something about groups. So the thing which we should finish is a metric tensor. So what is it? It is by definition a tensor of type 0, 2 in the linear space. So at the level of components, it is some GAB. And it has to be first symmetric, and second non-degenerate. Sometimes even positive definite, which is stronger than non-degenerate. So what does it mean symmetric, this one? It is abstractly this property. So if you change the order of the arguments, you get the same number like if you do not change the order. Yes? Well, these tensors are bilinear forms. They have special name. So this is a special bilinear form which is symmetric in this way. If you put the basis there, you get at the level of components that GAB equals GBA. Another way how to look at it, because they are just two indices, it can be viewed as a matrix. As this says that the matrix of the components is symmetric metric, yes, the matrix. So it is symmetric. So this is the first point. And the second point, first of all, the stronger one, that positive definite. You remember from linear algebra, it means that GVV is bigger or equal to 0 for any argument, and 0 only for 0 argument. So for non-zero vectors, it is positive, and for 0 vector, it is 0. But there is a more useful definition. This is, well, maybe older definition for metric tensor, but at least from the time when special relativity came to be interested in physics, we know that there are also objects like metric tensors which are not positive definite, and still they have all other properties and they are useful. And because of, I think that mainly because of that, there is a weaker condition, not positive definiteness, which goes to the definition. The definition of metric tensor, I think that mainly is meant that it is not necessary to be positive definite, but non-degenerate is important. And non-degenerate, well, there is a pedestrian definition that non-degenerate is the determinant of this matrix is not 0. But it is technical definition, and one can see more about it from some later development, which will be done now. Yes, that some other points of view what this means. But it can be done as a good definition. By the way, here is important, check that GAB is with respect to some basis. And what about other bases? You should check that this is good condition, that in other bases it's still determinant. Determinant still is not zero. That it cannot happen that in one basis determinant of the matrix of components is zero and in other bases is non-zero. Think over why it is. It is simple, but it is important. That is a correct definition. Now, what can be done and what usually is done when you have metric tensor? Actually, we will see that metric tensor is a very strong structure, both on linear spaces, on the level when we are now, and especially when we come to manifolds to do differential geometry, that it is very strong structure in the sense that it produces also other structures. That it is not only used in its direct way, like from the definition, but it induces other interesting structures also. Also in linear algebra a little bit, but on manifolds even more. So in this sense, it is very strong structure, that if you have metric tensor somewhere, you have a very strong structure, you can do a lot of things in general. So basic things is, it is used that this object is called scalar product. It is especially in the case if it is positive definite. That scalar product, in fact, is a metric tensor with two vectors inside. So then if we have scalar product, we can compute the length of vectors. Yes, this is square of the length of vector v. So this is a possibility to measure the length of vectors. Then you can compute angles between vectors. Yes, that there is a formula that GUV is the length of the first vector times the length of the second time cosine of alpha. It is definition of this alpha. Yes. So you see that a lot of things are based on the existence of metric tensor, but at the same time, you must understand that it is an additional structure to the linear space. That if you have linear space with metric tensor, it is a pair that first you have linear space without metric tensor, and then you add metric tensor, which enables you to do things which are not possible without metric tensor. So up to now, we did a lot of things of these tensors and so on without G. Yes, tensors exist also if there is no G. But if you add a G, which is a specific tensor, you can do other things. All things just with L, plus some new things which can be done based on existence of this G. And one of things is something which is called usually, especially in physics, but also in mathematics, that raising and lowering of indices. It is a very important procedure. In relativity is completely frequent. But what does it mean abstractly, and what does it mean how it is done actually? First, I will introduce some other tensor, which is a rather delicate story, so you must think it over. It is also an exercise in the book. By the way, everything which we are doing yet is 0.24 in the book. Section 2.4. Everything on the first lecture and second lecture was just section 2.4 in the book. So this section has something like 10 pages. Yes? So we are doing some 10 pages of the book still, and only after finishing this, we will go to chapter 10, a big leap. I will explain why. So still the end of the 2.4, and the thing which I will now explain is just an exercise here, something like 2.4.9 or something. I don't know by heart the number of this exercise, but it is in the middle of this section, and this is thing like that. That if we have GAB, we automatically have something which is called GAB. And how this comes? That GAB has non-zero determinant by definition. That means that we have also inverse metrics to these metrics. Yes? So let's define it by writing so what is written here? Let's now have a look as a matrix equation now. Yes, so what is here? It is product of two matrices, because it is CC, so it is matrix product. And the content of this equation is nothing more than this matrix and this matrix are mutually inverse, because by multiplication you obtain unit matrix. So let's use this notation that this is matrix G. It is not metric tensor, it is its matrix. This hat shows that it is its matrix. And let's this matrix, which is here, call capital G, just to work with matrices, because it is simpler. So this equation says that this and this is unit matrix. It is component expression of this simple equation, that they are just opposites. Now, this matrix depends on the choice of basis. Yes, GAB is abstract tensor G computed on this basis, we know. So, if we change basis, in standard way, using the change of basis matrix A, we know that what is the formula for changing of this? That GAB goes to AAC, ABD, and GCD. It was already done, which is GAB primed. And it can be written as a matrix equation that the matrix prime, this one, is given as A transposed G and A. Yes? And now, what does it mean? That this is matrix equation in some concrete basis, that this is GAB in basis E, but we can change the basis and obtain primed matrix here. And of course, if the original matrix changes, the inverse should change somehow. And we want to know how the inverse matrix changes. It is inverse to this new one. So we want to find this matrix from this equation. It is simple. Well, just G primed is what is AT G A, and this G primed should be 1. So I put, instead of matrix G hat primed, I put these results. Yes? So I obtain this equation. And from this equation, it is clear that what is this matrix, because it is product of 4 matrices, and all of them are non-singular, so they have inverse. So first, this goes away by multiplication from the left by AT to minus 1. Yes? So you can have a look that you have equation without this At is A to minus 1 transposed. Then you should multiply from the left by the inverse of this G, which is capital G. So we have just A G prime is capital G, A to minus 1 transposed. And the last step is multiply, but from the left by A to minus 1. And we get this important result, which we can now write down in terms of components. It is just matrix multiplication. So this matrix is G primed with upper indices. And the formula is A, B, C, D, G, C, D. You can check that these two equations are the same by content. Yes. But what does it mean now that we know this formula? This is the formula how components of tensors of type 2, 0 are transformed. Exactly. What does it mean? That whenever you have a tensor of type 2, 0, 2 invertible, then you obtain 2, 0 type tensor, which can be called GAB. And it is given by inverse matrix in any basis. So in one basis, you compute inverse matrix, and you obtain some new matrix. Yes? Then use this matrix as components of some tensor of type this one, not this one, but opposite. And it works. This computation shows that it works, that you already defined something interesting because it works in any basis. What I did was transformation to any basis and to show that really this guy transforms as it should be for tensor of 2 type, 2, 0 type, so opposite. So this is rather well, not completely trivial idea, so you have to think about it, that what we did, and I will tell that what is the result, and think over that really it was done, that whenever you have a tensor of type 0, 2, bilinear form, which has the property that its matrix in some basis is invertible. This is the second point. This tensor plus invertibility. Then do inverse matrix in the same basis and observe that this matrix behaves like components of tensor of 2, 0, not 0, 2. So we can construct this tensor by adding basis to it. This tensor was G AB EA EB, and this new tensor I call G to minus 1 in my book. In several sources it is noted, the notion this one is used, so I'm not original in it. I don't want to be original in notation. So there are different tensors. We started from metric tensor, and we constructed out of metric tensor this tensor. It is not metric tensor, it is different tensor because it is of different type. So it cannot be the same. And this is, this is called usually metric. In tensor is somehow not told, somehow yes, but not always, just metric. And this is called cometric. Cometric, yes. So the story is whenever you have metric, you have also cometric, yes, in short. So try to understand the idea behind this computation, that this computation discovers existence of this cometric. Okay, now how metric and cometric can be used for doing this computational racing library indices. But do you have some question? If you wanted to ask, feel free. Nothing. Okay. Okay, but whenever you have anything, you can ask. There are no stupid questions. It is just a myth that they exist. They do not exist. Fine. So we are going now to one procedure which is possible if you have metric. And the idea is quite simple and funny, that imagine this mapping. You know, there is a mathematical notation that whenever you see some dot somewhere, it means a slot for inserting something. So we have a vector. It is tensor of this type at the beginning, vector v. And we map it to this object. We have metric tensor. We inserted the vector to the first slot, and we have free second slot. So it is something which waits for the second slot to be filled with right argument, of course. And what can be put to the second slot? Another vector. Yes. So this is something which waits for vector, and if you give it vector, then this object puts you back a number. So it is some mapping that if you insert vector here, you get a number. But we know that there are some objects which eat vectors and produce numbers, and they are called covectors. Yes. So is it automatically covector, or should we check something that maybe it is not covector because it doesn't fulfill something important? Covector is a mapping. Vector goes to number, but with some property. And which is the property? Linearity. So is this slot linear? This is the question. And what is the answer? Yes, you know that yes, but why?
Because the metric
because metric is bilinear. Yes, bilinear means linear in both slots. Here is already filled, but this slot still lives, and it is linear because it was linear from the property of metric tensor. Yes, so there is a slot for vectors. This slot is linear, and the result is a number. Finito, we have a covector. Yes, so this is from 0, 1. What does it mean? That this is something from 1, 0 to 0, 1. And this something depends on metric tensor. It cannot be done without metric tensor. So we will denote it like usually it is. This is musical symbol. This. Like that. And why it is denoted by just this? Or I will go on with the cometric, very similar story, and then we will compute that we have a covector now from 0, 1, and we map it to the cometric, which waits to two vectors. Cometric is of type 2, 0, so it waits for two covectors. Two covectors, yes. So the first covector will be alpha, and the second will be just empty, as it was the case for the metric. What is it? It is something which waits for a covector to give us a number. It is an object from the dual of dual, but from the last lecture we know that we can identify it canonically with a vector. So practically this is a vector. Yes. So again we have a map. 0, 1 goes to 1, 0, which we will call by similar musical notation. It is not, unfortunately, it is not my invention. I would be proud if it were my invention, but it is unfortunately standard in the mathematics. Now we want to discover how it looks in components. So we want to compute, for example, this object, this covector. As each covector, it can be written like component times basis, yes, like vector other side. So how the component of alpha is computed? We know it, that if we have alpha, then alpha A is put EA to alpha. If you don't remember, then have a look, that it was computed like that. Yes? In order that this is true, this alpha A should be exactly this expression. So if we want to know what is this, what covector, we should obtain first its components and then add the basis. Yes, it is the same logic like here. Now, what is this? If you express it in the same basis, you see that VB goes out, and here you have GBA. So V, which is VAEA, goes by this mapping to GABVB and basis EA. So on the level of components, what happens is that something with those components goes to something with these components. Yes. So this is the reason why it is called lowering of indices. This is called operation of lowering of indices, because originally we have one index up, and at the end we have one index down. Of course, these summation indices do not matter. And you can check this formula that it works, that alpha A goes to G A B alpha B. So first we have index down, at the end we have index up. This is racing of indices. And now how it works in music, whether I never met this situation. But in principle, you can imagine that some author which will write something like that. What should I play now? Just A. This is unit operator. Yes? The same holds here. You can check it. It will be an exercise. It is very simple. Yes? So, in both orders, it is unit operator. So they are mutually inverse operations, raising and lowering indices. Okay, everything else is in exercises, but there is some maybe important note, quite important, that we used for both raising and inverse and lowering indices, metric tensor. When we used its properties, or which properties of metric tensor were really important in this construction. There are two properties, symmetry and non-degeneracy. If we do this, you see the formula. Imagine that GAB is not symmetric. Is it some big problem? And imagine that we have no non-degeneracy, so inverse matrix does not exist. Is it a big problem or not? Yes, cometric does not exist. And what does it mean? That if our GAB were not non-degenerate, if it is degenerate, we have no inverse matrix, then what happens? What we can do and what we cannot do. Is it defined, this operation, then? Yes, it is defined. And can you raise backwards the index? Not. So this is the problem, yes, that if you have, so the non-degeneracy is important when you want sometimes to put it back. But symmetry is not that important, actually. Yes? And it is really used that in chapter 14 we will study something which is called symplectic geometry. It is important geometry for understanding Hamiltonian mechanics. And in symplectic geometry, the basic object is something like metric tensor, but it is anti-symmetric. It has also symmetry, but skew symmetry. It gets minus, yes, if you change indices. But if you imagine that this will be anti-symmetric, nothing important happens. Yes? And this symplectic form, which is called there, has an inverse, so it is non-degenerate. So symplectic form, something else like metric tensor, can be used to raise and lower indices as well as we do it with metric tensor. Yes? So it is quite useful to understand that what part of your structure you actually use if you do something. So this is an example of much more situations that if you do something, think it over what part of your structure you actually used, whether it can be used in some other place with other guys. Yes? I think that I will have a look what is here, right? Yes, metric tensor raising and lowering indices. We know what is it. Some details can be done on the recitations through exercises. They should be done. So now, if anything was not clear and you want to ask anything from this part up to now, tensors and so on, you have a time to ask, because then I will go to chapter 10 directly. This was from chapter 1, but you see that it is not from the very beginning of the book, because before it there is a definition of a manifold and important things for differential geometry. But I decided for this course to not to be very strict in this order, because for this course, I think it is better first to be clear what is tensor in linear algebra, and then study manifolds and things like that. Then come to the concept what is a vector on the manifold, and then automatically put to work this machinery of tensors, and everything is clear how tensors on manifolds come from tensors in linear from vectors on manifolds. Yes, we will see that the concept of vector on manifold is rather tricky. It is not very simple. So we must pay attention how to define the concept of vector, but as soon as we know what is a vector on a manifold, which needs a lot of work, what is a tensor on manifold, then it is very, very simple, because we are already prepared what are tensors for general linear space L. So we use just some particular linear space which sits on manifold, and what we will have tensor machinery on manifolds very quickly from vector machinery. Yes, this was the reason why I wanted to start with tensors in linear algebra, to finish it, to settle it in your brain for some time, and then to go on with different topics, manifold, first linear some groups, matrix groups, which are also important, and only then to come to manifolds and use it on manifolds. Not to make a big side steps there. Otherwise, as in the book, you first learn what is a manifold, what is a vector on manifold, then you have 10 pages of this about tensor, and then you go on that what about tensors on manifold. Yes, so there is another possibility. First study 2, 4, and then go to manifolds. So are there questions to tensors and anything which was done? If no questions, so I go to this second week, and the second week is basic metrics Lie groups, which is the title of the week. And the first line is symmetries or automorphisms of various structures and groups. So it is not symmetries of groups, but symmetries of something and groups. And plus examples, of course. So I just repeat perhaps that what is a group? It is a set mass. What is there? There is a multiplication. If A and B are from G, then there is something like AB. And there it is called that we did multiplication there. But it is just a prescription to construct the third element for first and second element, binary operation. It has several properties, not too much. It is associative, this product. It is not commutative by definition, so I don't write it. There exists a unit element, which is funny property for multiplication, that multiplication of this funny element with anything is this anything. And it doesn't depend even, well, whether from right or left. It can be shown that if it works for this right multiplication, then automatically it works for left. So this is not independent definition, actually. And then exists for each A, there exists A to minus 1, such that the product, once again, in all possibilities, gives this unit element. Nothing more. So it is extremely short list of definitions. What is a group? And it is fascinating how many applications such simple set of definitions can produce. That they are thick books about groups, representations, I don't know, all actions, and really is a big stuff in mathematics. So this is the ideal situation in mathematics, that you define something very, very quickly in several lines, and then you can study it several years. And it is still something not studied. Yes? The opposite situation is a little bit tragedy, that you define something on 3 blackboards, and there you have just one example on this object, and very trivial. So this is ideal situation in mathematics, in my opinion. Now, okay, and why it is so important? So I think that the main reason is that if you have any set and you study bijections from any set to the same set. Yes. And you can combine them. So let's have the set n and one bijection and second bijection, and then compose them. Yes. So it is again a bijection, clearly, because bijection combines elements in both sets, and it is something like permutation. For finite set, it is called permutation. For general set, it is called bijection. And you know, if you have a look somewhere for groups, one of the first example of groups will be the group of permutations. So group of bijections is well-known group, yes, and this is the case not only for finite sets, but for any sets that study bijections of these sets. And what is important, that composition of these bijections is again bijection, which is highly trivial in my opinion, yes, clear. Yes, and there is also a bijection which is trivial completely, that do nothing with the set. Identical mapping. There's general f does something. And a very specific element of these bijections does simply nothing. And of course, if you do something, you can go back because it is bijection. So there exists f2 minus 1. And now you see that we obtained naturally a group. When the elements of the group are the bijections, and the composition plays the role of multiplication. And check that this holds. Maybe it is not completely clear from the very beginning, but apply it on some element and you will see that it is trivially fulfilled. So we have everything which we need for a group. So we have a group, bijections of a set M. For any set, you have very specific group, its bijections. This is not the most interesting group, because usually you do not see sets without some additional structure. If you study some set, it should be somehow interesting, and this interesting part of the set is usually done by the structure on the set. Yes? So imagine we have some set and some structure, this pair. It is structured set. Then we can still try to find bijections of this M. S doesn't exist, but more interesting bijections will be such that so-called they preserve the structure. So we study f m to m bijection, first of all, and second, preserves the structure S. What does it mean? Now I do not explain. We will give important examples, and we will compute these groups for important examples. So, first of all, you find all bijections, and then you will test. The first one preserves the structure. Yes. Okay, come here. The second one, do you preserve structure? No. Go away. Yes. And you will just leave those F's from all bijections which have additional properties too, that they preserve the structure. Now, these guys who are here, who preserve the structure, they also create some group or not. What do you think? So if you compose two structures, two mappings which preserve the structure, do you once again obtain from this composition a mapping which preserves structure or not? What do you think? I didn't say what does it mean, preserve structure, so it is rather hand-waving talk, but in spite of that, by so-called feeling, now it is very good word, that I feel something. So what do you feel? That composition of two mappings which preserve structure, do preserve structure or not? We can think like that in the first step, where composition have two steps, yes, that first one, second one. In the first step, I did the mapping and I preserved the structure. So structure is still there, preserved. In the second step, I do the second mapping, I still preserve the structure, so structure is still there and still preserved, like it was after the first step. So after the two steps, the structure is intact. It is like it was. Yes, so just intuition and I don't know what says us that if both of these mappings preserve the structure, so their composition should also preserve the structure. And what does it mean? That we obtained another group, not group of all bijections, but group of those bijections which preserve the structure. And at the same set, you can define several structures, often. So for each structure, you have separate group. Group which preserves structure number 1. Group which preserves structure number 2 at the same set. They can be different. And you can also speak of stronger structure. If you have, say, S1, S2, some two structures, you find the group which preserves S1. And then you say, I want also to preserve, except for S1, also to preserve S2. So some mappings which preserve S1 are bad from the point of view of S2. So they go away. And what is still there are only mappings which preserve that and also that. So now, is it clear, I hope, that this group which preserves nothing, this just one, is bigger than the group which preserves something? Yes, because some mappings went away, were not allowed to come to our group. And if you preserved already S1 and you add some S2, the group is not bigger but lower or smaller. Yes. Once again, we cannot measure what does it mean smaller yet, but not all elements which preserve S1 are good for also preserving S2. So the tendency is that as you add additional structures, your group is smaller and smaller, in principle. I think that it is quite clear. Okay, now have a look on what this structure could be. Everything which studies mathematics is some structure. Yes, so this story is extremely general. What I told now, it is true for everything you learn in mathematics and big part of what you learn in physics. So important examples for our course. First of all, let our MS will be this linear structure which we started with the preceding two lectures. So linear space is a set with some structure. Now, what is this structure? Well, what I mean by there is some structure, it means that you can do something in very, very brief language. You can do something more than you can do in the set. Yes? You can do something interesting there. So what we can do in linear space, except that say that some vector is there and this is there, because this is the structure of the set, that what is there and what is not there. Yes? And what is the additional structure which comes from the concept of linear space? What we can do there with elements?
Make linear combinations.
Yes. So from V, W, and lambda, we can do this. Yes? This is the structure present in linear space. So now we have, imagine that we have mappings from L to L. They are these Fs. And we want such mappings which are bijections, first, and second, that they preserve the structure given by linear combinations. So what does it mean? That if you do linear combination on the result, it should be the same like if you do it on the building blocks. This means that, by definition, that we preserve the linear structure on our set. Then you map three things, V, W, and V plus lambda W, and there is this correlation between these images. Now, okay, these are, so this is preservation of the structure and exists A to minus 1, it is bijection. Yes? So, what is it? Do you know this property with some name? Is it a well-known property or it is something which we just learned? It's linearity, nothing more. Yes? So, what are the interesting mappings in the linear space? Linear mappings, of course. Yes? That's why they are studied in linear algebra. That linear mappings are typical for linear spaces. Yes? So, this is the reason why we study there in big detail. And now, if we want to study groups, not all linear mappings are interesting, but bijections, which mean invertible linear mappings. Not all linear mappings L to L are invertible. So our G, our group of interest, which preserves structure of linear space, is group that invertible linear mappings. And the group has its own, his separate name, GL. Oh, our vector space will be V, because otherwise here should be LL, and it is not very nice. So GLV. And it is abbreviation of general linear. As you see, it is not very general because it is invertible. There are linear mappings which are non-invertible, so actually the word is strange, the name, or I do not understand something, but general invertible is important. And I will also write this notation, that the same group is the group of automorphisms of this vector space. So what is automorphism? Morphism means that you preserve structure in general. And automorphism means that it is mapping to the same set. So combination is that it is, well, now from V to V, yes, which that means it is this auto part, and morphism which has this property. So altogether this and this is automorphism. But this name doesn't say you how it looks like. Here is the answer, that what are automorphisms of V? General linear transformations. We already did some computation, so-called, and we found that, oh, it is our old friend from the first year, linear transformation. So this is the difference between these two names, that here is definition of what we want, and here is more or less the answer, that this guy, what you want is this. Now we can go to, for example, another example, just by hand waving. We can have linear space now over other things like real numbers. For example, over complex numbers. We can study complex linear algebra. Yes? So our basic object will be complex linear space. What is the difference? Just here, that here is now a complex number, or something else if we want some fields and so on. So complex vector spaces are very similar, but they have different group because they should preserve complex linear combinations. We can have a look after a while. Now we should think that, or we should explain that there is some isomorphism of groups, and which groups, that we already know that this GLV is abstract group of abstract vector space and its mappings. Now, if we take this vector space and choose a basis, then this linear mapping is given by a matrix. This is the definition of the matrix. Yes? Actually, if you have a look to the components, you see that the picture is like that. That this is the definition, that you should map the first vector and then do this multiplication and have a look at what is the result this by this. Yes. So now what is important, that whenever we have abstract linear mapping A from our group and we choose a basis, we have also some metrics, unique metrics. And now we have another group, that group of these matrices. Yes. Whenever you have these metrics, because this abstract A could be reversed, so we can go back from this to original E, and that means that this matrix should be invertible matrix. That means its determinant is not zero, invertible. But now invertible matrix, this is invertible linear operator, abstract. So now we have a bijection given by choosing a basis. Within this basis approach, we have bijection, abstract linear mapping with elements of the group of invertible matrices. Invertible matrices are called GL and R. Yes, this is also group. How this group works? Elements are invertible matrices. What is the multiplication in the group? It is matrix multiplication. And now the statement is that these two groups are isomorphic. So GLV is isomorphic to GL and R. They are quite different groups. This is abstract group of all invertible linear mappings. This is group of n by n matrices which are invertible. With multiplication here is composition of mappings, and multiplication here is multiplication of matrices by well-known rule. And how it works? If we have composition of AB and apply it to EA, so it is A applied to B applied to EA. This gives us matrix. These are numbers, so linear mapping A jumps all these numbers. And A comes to this basis and produces a matrix, namely A, C, B, E, B. So this is first, second. This should produce matrix of this composition. So we see that these two results should be the same. And if you have a look, it is told that if you compose linear mappings, you just multiply the corresponding matrices. So this is actually the reason why matrices are multiplied as they used to be. Yes. This is not accident that you multiply matrices by this strange way. It is just we want that they correspond to the multiplication in the group GLV, so composition of mappings. And this is actually the proof that these two groups are isomorphic. When two groups are isomorphic, when you have, this is definition, when you have a mapping from the first to the second, which is invertible, it is bijection, and it preserves multiplication. So I officially, you have some mapping from first group to the second group, such that if you multiply here two elements, the result is the same as if you multiply the images of these two elements. Here the multiplication is within the first group. Here the multiplication is already within the second group. It can be completely different multiplication. So this is called homomorphism, and if it is invertible, it is by definition isomorphism of groups. And what we see here, this computation shows that this happens actually in our example, and this bijection is by definition here. Well, what is the difference between the matrix group here, if you apply this matrix technology on complex linear space? What will be the difference? If we have complex linear space and we want to introduce matrices there, if you put some matrix, can you see that this matrix is a matrix from complex linear space or a real linear space? Or other question, is it visible somehow that you use matrices from complex linear space or real linear space? I hope that. Sorry? Sorry? If it is real and if it is complex vector space, then they are complex. Yes, so that's simple. Yes, that if you see somewhere complex matrices, it means that its elements are complex numbers. It cannot be a matrix of a real vector space and automorphism. Yes, but if you see a real matrix, it is tricky. It can be matrix in complex space. Yes, because the complex matrix as a special case can be real. So the other way it is tricky. If you see complex matrix, you are clear that it cannot be matrix of a real linear space directly. I mean, by some trick maybe. And there is an exercise which I will offer to this recitation, that if you have complex matrix, you can always write it in terms of two real matrices. It is trivial. And if you compose matrix, I don't know by heart, but something like B, C minus C and B, I think. I'm not completely sure, but so I could remember, but it is not important now. Something like that. And then you multiply those matrices, you effectively multiply complex matrices. What is the lesson? That the complex n by n matrices can be mapped to twice bigger real matrices, and the multiplication works. It is isomorphic to matrices of this type somehow. So complex matrices can be used as real matrices, in the sense that some real matrices play the role of complex matrices. If you have a look to this example, you will be clear that what I want to say. But actually what I wanted to say that the group of real matrix group is the most interesting one. That also the group of complex matrices is inside. Now, what about the case when we add some interesting structure to the structure which is already there? So our MS now will be vector space with a bilinear form. So we know that already the structure of vector space is interesting. It gives us the two groups which are isomorphic, GLV and GLNR. And now, what do we obtain if we have bigger structure or stronger structure? That we still can do linear combinations, but we also can compute something like scalar products, yes? But yet it is general bilinear form. So we should preserve first of all the structure, which already we know what we should do actually, plus, so we should restrict to linear mappings, linear invertible mappings. And now what about this bilinear form? So what do we do with bilinear form? We usually put two vectors in it. This is the aim, to introduce bilinear form, to fill it and obtain numbers. Yes. And now, what is the most natural construction to be claimed to be the preservation of H? If we interpret this as a scalar product, then we can define interesting A's interesting linear transformation such that if you apply this linear transformation to both arguments, the scalar product will be the same. Yes? So this should be H on AV and AW. This is restriction on these A's. Now, this is given, and these two guys are any. So we want to define such linear mappings which have this property for given H and for any vector V and any vector W, because we want the preservation of scalar products of any pair. So we can now check explicitly that if you have some A with this property and some B with this property, then also multiplication has this property, which is already trivial. We know that it should be the case, that if one transformation preserves the structure, another one preserves the structure, also composition should preserve the structure. Yes? So imagine that also for B it is the case, just to do formal proof that such linear transformations really form a group. That we have some B with the same property, and the claim is that their composition has also the same property. Yes, so compute composition AB applied to V and AB applied to W. What is it? Well, it is, let's call it some U. So also here, here is not, here is some what U tilde. Yes. So it is H computed on AU, U tilde. But A should be cancelled because it has this property, or can be cancelled. Yes? So it works also without A because of this property. Now there is B applied on V and W. Because of the second property, we can also cancel it. So we see that it is HVW. So we see that whenever you have two linear transformations which preserve H in this sense, their composition also preserves the structure. And because they are both invertible, also the composition is invertible, so we had a group. We had a group which is smaller than the group of all invertible linear mappings, because we want something else from them. Now, what about matrices? We can simplify the computation, that notice that this is some number and this is some number which are equal, and this number depends on V, for example, here, and also on V here. And notice that it is linear in this V, because here it is in a tensor, and here it is first in linear operator and then in a tensor, which is another linear mapping. So that's why this expression and this expression is linear in V. Also, they are linear in W. Then the consequence is that if you prove, or if you expect validity just on basis, then you have automatically validity of this on arbitrary vectors. Yes? So if you write this equation only on basis, it has the same value as if I would write it on arbitrary vectors as is there. Is it clear that from this equation you have also this? And it is completely clear that from this equation you have that, because you can put V equal EA and U equal VB. but the backward is a little more tricky, that you should add, multiply it by VA and VB, yes, and you will get this. So let's start with this property which is equivalent to that. What is this? This is something denoted by H and B, and if you remember from the lecture of linear algebra in first year, it is called the matrix of the bilinear form. In our language, is equivalently, now it is AB component of this tensor, by definition. By first definition, in the first year, it is matrix of the bilinear form in this basis. According to our definition, it is AB component of the tensor H in this basis, which is the same. Now, here you have definition of the matrix. Here it is A, B, D, E, D. Then bilinearity. And what is remaining? H, C, D. So the equation is this one. So the interesting matrices of these interesting, so matrices of those interesting linear mappings should fulfill this equation. Now, you can notice that it is, if we treat it as matrices, there is some matrix multiplication. We already met it yesterday. What multiplication? Namely, transposed H A B. So the matrix H with these components should be equal to matrix transposed, matrix H again, and matrix A. So this is matrix realization of this abstract property. Do not forget or distinguish abstract objects and their matrices. Matrices depend on basis, and this doesn't depend on anything. Now, there are two interesting possibilities. One of them is even more interesting, that up to now this was a general bilinear form. So this matrix is a general matrix which can be assigned with general bilinear form. But much more interesting case is when this bilinear form is symmetric and non-degenerate. So from now on, H symmetric and non-degenerate. Then it can be simplified a lot, and it is the most interesting case among these bilinear forms. There is also interesting case with when it is antisymmetric, but we will not study it here. It is studied in chapter 14 with connection with the symplectic form, symplectic geometry, which I mentioned. That is interesting for Hamiltonian mechanics. But for now, it is not interesting for us, but symmetric bilinear forms are interesting. And we will just remember you that there is a theory of symmetric bilinear forms, which you know, that you can choose a basis in special basis. You can somehow optimize the matrix of a symmetric bilinear form and put it to so-called canonical form. Yes? And what is this canonical form? Do you remember that if you have general symmetric bilinear form, real, what optimal matrix it can gain in optimal basis? Sorry?
A diagonal.
Yes.
With wells minus ones.
Exactly. So here is unit matrix, a block, which means here are ones. There is another block with minus ones and the rest with zeros. Yes, and otherwise 0. Yes. And these two blocks are unrelated. So this is Q by Q, say, or R cross R, and this is S cross S. And the remaining is in order to fill the matrix. So now, if we have non-degenerate bilinear form, what happens to this general case? This is general case for symmetric bilinear form. And how you can see, if you do this matrix, this optimal one, how you can see that it is non-degenerate or degenerate? No zeros. So, exactly, yes, you are right. If it is non-degenerate, there could be just non-zero numbers. And even it is positive definite, if it is positive definite, there are no minuses. Yes? So in this optimal form of this matrix, in this canonical form, it is clear from the first sight that this is the nice property of canonical forms, that you have a look, okay, I see everything from canonical form. So this matrix without zeros, just this matrix, will be called eta matrix. Eta is standard notation in special relativity. Yes, some concrete eta, 1 minus 1 minus 1 minus 1 or something like that, or opposite. But also in mathematics, in more general physics, eta is this kind of matrix, that several ones, several minus ones, and no zeros on diagonal, and zeros outside diagonal. So this H is up to now general. Now we restricted it to symmetric non-degenerate. So we can always find a basis in which this H as a matrix is this eta matrix. Yes? So if it is not, it is our fault that we didn't pay attention to good basis. We complicate the equation in bad basis. But in good basis, we can rewrite this as eta equal transposed eta A. Yes. Or if you even go further and have this positive definite case, there is no eta, but what happens from eta when you have no minuses? What matrix it is? Identity matrix. So imagine that we have positive definite case. So here you have unit matrix, and also here you have unit matrix. But unit matrix here does mean that they are just neighbors AT and A. Nothing is inside. Why to write it, this unit matrix? So for positive definite case, the equation is unit matrix is ATA. And this is well-known equation from linear algebra for you, I hope, that you know matrices which have this property. What is the name of such matrices? Yes. So they are orthogonal matrices. And they are called ON in n-dimensional space. And those matrices here are something like pseudo-orthogonal, and they are called ORS. If here is R by R and S by S unit. So we have other interesting groups, and this ON is in fact n0, yes, in this notation. So On is just special case of On, ORS, On n prime, say, with the second number equals 0, because the second number is number of minuses there. So these are names of these groups, and these are equations defining these groups. Yes. Then it is a very interesting group in the linear space. When we have structure this and volume, the techniques for it is more advanced. It is done in chapter 5 in my books. You need something which is called forms for it to understand it really. So you can wait to the next year, the mathematical physics 2, for the technical part of this, but the content is not so problematic. So imagine you have a vector space V and several linearly independent vectors, and now you create something which is called parallel epiped, something like that. Well, for 3 vectors is like that, and imagine for 4, 5, and so on. And you want to compute volume of this object. It is some number. If these vectors are ABC, some number constructed from ABC. And if you have more dimensions or more vectors. And now, important thing is that imagine that you have a linear mapping A, like here, and you act by this linear mapping on each of these vectors. The same A applied to each vectors here. So you get another object. This is parallel epiped based on ABC, and you now parallel epiped based on AA, AB, AC, and if more on each one. So you get a new body, and this new body has a new volume. So, but it turns out that the volume of A of this guy is determinant of A time volume of the original one. By this I mean that apply A on each vector, yes? So this is the new volume after application of A, and this is the old volume before application of A. And it turns out that it is that simple, that this is the meaning of determinant, that how the volumes change if you apply this linear mapping on each vector from which this body is composed. So now we see that there is a potentially new interesting group, that what A's do not change the volume. They change the body, yes, but they can not change the volume. That you can imagine, for example, in 2 dimensions, you have something like that, and the volume is this area. But you can make twice this and 1/2 of this, and it has the same area. So something more dimensional can happen, and happens, really. So the interesting linear transformations are those which preserve the volume. It has nothing to do about lengths, angles, individual vectors, but just volumes are important. So what is the elementary property of this group? How can we specify technically this group? The group of linear transformations which preserve volume. After this knowledge, how is it specified? Exactly. So SL V or SL and R is determinant of A equals 1. Yes? A new group. it is the letters are special linear, and here is orthogonal, and here is general linear. Yes, special linear is special in this sense that it preserves volumes by definition. And now they can be combined, that you can have orthogonal and at the same time preserves volume. There is, by the way, some small tricky point that this preserves a so-called oriented volume. I didn't specify it. What is it? It is in chapter 5. So there is a bit tricky point. I will not explain. So that's why orthogonal group can change volume, which is surprising, but only to minus the same volume. Yes, and the subgroup of orthogonal group which doesn't change this minus, doesn't produce this minus, is called then SON. Yes, this special orthogonal. So this is the end of today's lecture.